2. Okay. So now today we're going to do 4 sessions. Remember, one is brought forward from tomorrow. On the third topic, and this is organometallic reagents. And remember, the 3 topics are dealing with situations where it's not easy to think in terms of electrophile, nucleophile. The mechanisms don't neatly fit into that. And here we're going to be looking at catalytic cycles. And this, of course, this area of organometallic reagents, coupling reactions, and metathesis has grown enormously in the last 10 to 15 years. So what I'm going to look at is so lectures 9, 10, 11 and 12, that's numbered in sequence since last Monday, will be today, and then we'll do a final one in this block tomorrow. So the first session now is going to introduce the D block transition metals, a bit about metal ligand bonding. I'm an organic chemist, so you're not going to get a very theoretical or inorganic view of this. You're going to get my view of this. And then talk about some palladium catalyzed coupling reactions. The second session will continue talking about palladium reactions. And then tomorrow we'll look at, I beg your pardon, this afternoon, lectures 11 and 12, we'll look at ruthenium catalyzed reactions, which really in this context means metathesis reactions, and then a little bit about gold mediated reactions towards the end of this afternoon. So that's the program for this block, as you might call it. So we should begin this first session before our break talking about introduction to D block transition metals, metal ligand bonding, and talking about some palladium catalyzed coupling reactions, in particular in this first session, the Heck and Stille reactions. So here we have the transition metal and lanthanide blocks, and just to place the metals we're going to look at in context, you can see palladium there marked in red, you can see ruthenium in blue, and gold in the bottom row in yellow. This shows where they fit into the periodic table, into those transition metals. And if you were looking at learning outcomes for most university type courses in this area these days, you would see the learning outcomes that are listed above, an understanding of the importance, so that you should gain an understanding of the importance of organometallic chemistry and contemporary organic synthesis. We're going to see a lot of examples of where that's been used, to recognize the key steps within any palladium, ruthenium or gold catalyzed reaction, and rationally devise plausible mechanisms and catalytic cycles. So that's what I hope you can gain out of what we're going to do in these lectures, and then look at examples of applying that to the synthesis of complex molecules. So we're going to take those metals in a sense in order: palladium, ruthenium, gold. Just to remind you something about electronic structure, generally in a chemical environment, an s orbital in a certain shell is higher in energy than the d orbitals of the shell below. So if you look in the top row there, written titanium, I'm writing it as 3d2, 4s2. So because the s orbital is really higher in energy, we can regard that as 3d4 in its outer shell. And it's the d orbitals that we're concerned with here, to give us the unique chemistry of the transition metals. And because those d orbitals are only partially occupied until we get to the right-hand side, zinc, cadmium, mercury, etc., then we get the possibility of a mixture of filled orbitals and empty orbitals, and that allows us to have electron donor and acceptor properties. Another thing we should think about is that transition metals like to achieve 18 valence electrons, 18 electrons in their outer shell. So if you look at a couple of, or a complex there, nickel tetracarbonyl has 18 electrons. How is that made up? It's 3d8-4s2, so that accounts for 10 valence shell electrons, and 4 carbon monoxide ligands, and they bind through what can be regarded as the electron pair on the carbon of carbon monoxide, and that provides then another 8 electrons to make a total of 18. Zero valent or nickel zero complex, nickel cyclooctadiene, 2 of those, that again has 18 electrons, 3d8-4s2, and 2 cyclooctadiene ligands, each of which is providing 4 pi electrons, because 2 of the bonds in the double bonds in the cyclooctadiene complex in each cyclooctadiene complex to the nickel. So we're looking to find 18 electron rule. General transition metals will attempt to attain 18 valence electrons when forming complexes. But if you can read that line at the bottom, it's not a foolproof situation. So there are cases where transition metals don't have 18 electrons, but more often than not they're trying to achieve 18 electrons. And if there aren't 18 electrons, then reactivity arises. And certainly in some of the palladium cycles we'll make use of that. Now the d orbitals I spoke about, just to remind you what the d orbitals look like. There's the dz squared orbital, there's the dx squared minus y squared orbital, where the lobes of the orbital are along the various axes. Then we have 3 combinations where the lobes of the orbitals can be regarded as being between a pair of axes, and so we've got dyz, dxy, and dzx. So that's the set of orbitals we're dealing with. So a mixed set of geometries, some of which will come in when I look at bonding. So this is a simplistic organic chemist's view of bonding. So here will be metal carbonyls, where carbon monoxide is the ligand, is carbon monoxide, and you can regard it as C minus triple bond O plus. And that means, so the C minus, if you like, is a lone pair on the carbon in an sp orbital. So that's a filled orbital. And then we have lots of pi bonds, but we also have pi anti-bonding orbitals. So I've drawn there, that says pi star, it's a bit fuzzy on the screen. But this is an anti-bonding pi orbital here. So we have an empty orbital and we have a filled orbital. And that will match in complexation with a filled d orbital and an empty orbital on the metal. So that you can have complexation where these two filled and empty pair have a sort of sigma type overlap, and then you have the filled d orbitals on the metal interacting with the empty pi star orbitals on the carbon monoxide. So that's a way of explaining the complexation. We have sigma bonding, donation of electrons from the ligand to an empty orbital on the metal, that's here to here, and we have pi bonding, donation of electrons from the d orbital on the metal to an empty pi orbital on the ligand, so the pi anti-bonding orbital in this case. You can do a similar thing with alkenes to form alkene complexes, and so again the same filled d orbitals, vacant orbital on the metal. The corresponding situation with an alkene would be an empty pi star orbital again. The filled orbital now will be the pi bond orbital. So to get that interaction, we've got to sort of turn the metal sideways, turn the alkene sideways, so the pi bonding orbital can interact with empty orbitals on the metal, and the filled d orbitals on the metal can interact with the anti-bonding orbital of the pi bond. So it's sort of sideways on complexation. This term at the bottom, synergistic bonding, is really saying that the two types of bonding, the sigma bonding donation from the ligand and the pi bonding donation from the metal to the ligand, are operating in opposite directions, but they are producing the same result. So they are reinforcing each other. A type of ligand that we'll see in many of the catalytic cycles is a phosphine type ligand. And here what we're looking at, same situation with the metal, filled d orbitals, and there are empty orbitals. On the ligand we're going to have a lone pair on phosphorus, so that's our filled sigma type orbital, and we're going to have empty sigma anti-bonding orbitals along from each of these groups, along each of these bond directions of the groups around phosphorus. So we have a number of empty sigma star orbitals that can, sigma anti-bonding orbitals that can participate. So you can see the picture now, filled and empty orbitals on the metal, filled and empty orbitals on the ligand, and you can see how that will give the same type of synergistic bonding. And with the phosphorus you can set up a scale of sigma donation, in other words how good they are at forming these sigma type donor bonds, and therefore in the complexes. I mentioned when we were talking about N-heterocyclic carbenes that the carbene-carbon in those systems is a sigma donor, and hence, I haven't drawn it here, but hence why the N-heterocyclic carbenes can also, or can replace phosphorus in many complexes. We can do the same things with alkynes, as well as we did with alkenes. Turn them on their side, and again we've got filled pi orbitals, empty pi anti-bonding orbitals, and the same synergistic bonding with metals. So pi to sigma donation from the alkyne, and D to pi star donation, pi type donation from the alkyne. Now you don't necessarily need to remember all of that, but all I'm just trying to show is how the ligand bonding can occur with transition metals and the significance of d orbitals to that. When it comes to the chemistry, that's underlying, and we don't have to be looking at that all the time. Now the first bits I'm going to talk about in this session and the next one are palladium catalyzed cross couplings. And the importance of the growth of this area was recognized in 2010 by the joint award of Nobel Prize to Heck, who has a reaction named after him, Negishi, we'll see Negishi's contribution in the second session today, and Suzuki, and we'll see his contribution in the second session as well. Stille, whose reaction I mentioned earlier, unfortunately passed away, so as I mentioned with Woodward, did not get a Nobel Prize because they can't be awarded posthumously. So let's look at that. Let's take the Heck reaction first. It's slightly different to the Stille, Suzuki, etc. So what we're looking at is coupling an organic group carrying a leaving group with an alkene, catalyzed by palladium. So that's a very general expression of it. The group that can be involved in the coupling can be alkenine, it can be aryl, not so usually alkyl, although that is just about possible nowadays. But originally these were sp2 type linkages to the leaving group being a halide or a triflate. The alkene that it's coupling to can be part of an aromatic, substituted with an aromatic ring, an alkyl, or an alkenyl, or a withdrawing group, and so on. So most alkenes could take part. And here's the sort of thing that could happen. This is an aromatic iodide, so this is your R1X component, and the carbon carrying the iodine is linked 1, 2, 3, 4, 5, 6, linked to this position on the alkene. Now notice that the alkene you get in the product is not in the same place as it would have been in the starting material, which would be down there. And the way that the alkene is broken and then reforms in this mechanism, and you'll see why the position of the alkene in the product isn't always reflective of where it starts. These processes need palladium 2, these processes need palladium 0, and we're starting here with palladium 2. But I should make the point that palladium 2, in the presence of triphenyl phosphine, or other phosphines, is actually reduced. And at the bottom here, we show how that, one way of looking at how that might happen. Here's palladium 2 acetate. The palladium 2 can pick up 2 triphenylphosphines as a ligand. You can get a reductive elimination between 2 of those ligands to give you an acetoxyphosphonium salt, which hydrolyzes to triphenylphosphine oxide and acetic acid, ethanoic acid. That would leave, that's a reductive elimination, so it leaves palladium 0 with 1 phosphine, 1 acetate ligand left, and that, for example, might exchange the remaining acetate for another phosphine. So we can end up having started,
in the second step, there is one acetate attached to palladium, so I think this oxidation state would be 1. So here you have shown you.
Well, this one?
Next.
That one? Next one? got me there. You might be right, but it certainly ends up at palladium 0. Yeah, you might have a point there. I'll need to think about that. As I said, I'm an organic chemist, so I'm just taking this on trust from elsewhere. Yeah, you may have a point. Certainly, but I think that what I'm trying to get at is that you end up with palladium 0. So even if you, I suppose the general point is, regardless of how it happens, which that may be wrongly written, we are going from palladium 2 reductively to palladium 0. Now, if you have a reductive elimination, you're going to you should have an oxidation state change of 2. Now, I think that is correct. However, I'll check that. But as I say, the overall point is that palladium 0 is the active catalyst, and this is if you like, a pre-catalyst situation. So we need to think about how this is happening. So whether you put in palladium 0 directly, that example I showed had palladium acetate, but it is possible to put in palladium 0 complexes directly. But either way, if you put in palladium 0 or palladium 2 in the presence of a reducing situation like triphenylphosphine or phosphines in general, the idea is you end up with a palladium with a number of ligands around it. It seems likely that the palladium here is either 14 or 16 electrons, and of course that would depend on how many ligands there are. In one sense, it doesn't really matter. In another sense, I can't be too definite here because I think nobody exactly knows, and it's probably a mixture of possibilities. But the key is we have palladium 0 can do an oxidative addition, effectively inserting into the bond between an organic group and a leaving group. Let's say that's a halide, to give a palladium 2 complex where the organic group and the leaving group are both are now extra ligands on the palladium. What happens next is effectively an addition across the alkene that is going into the Heck reaction. So that's one of the substrates, this is the other substrate, and you get effectively an addition across here where palladium adds to one, or it ends up bonded by addition to one end of the alkene, and the the organic group on the other end. So that's called a migratory insertion because the alkene is inserted between the palladium and the organic group. And if you look at it the other way round, you can regard it as an addition across the alkene. Now, a key point to note here is the stereochemistry. The addition is syn, so the organic group and the palladium add on to the same face of the alkene. That's going to matter because we now want to get the alkene back again because we formed a new carbon-carbon bond. So here's our organic group, here's our alkene. So we formed a new carbon-carbon bond, but we don't really want to end up with this carbon-palladium bond, and we want the palladium to be catalytic here. But we can't get the sort of reverse of the addition that happened until there is a CC bond rotation. Because what we want to, we could reverse the way but that's no good going back the way we came. What we want to do is eliminate palladium and something else, ideally palladium, well not ideally, but we want to eliminate palladium and hydrogen to get a palladium hydride complex. To do that, the geometry of the eliminating groups, the hydrogen and the palladium, has to be the same as the geometry of the groups when they added, when it was an organic group and a palladium. So we have to be able to have a bond rotation to get the palladium and hydrogen syn to one another. And then you get a syn palladium hydride elimination. So if you like, these across the system, these look equivalent to each other. But one has the organic group on the palladium and the hydrogen on the alkene, effectively. And the other side, we have the hydrogen on the palladium and the organic group on the alkene. We still have palladium 2 here, so we have a reductive elimination across there, usually with an added base, because you're trying to eliminate H and a leaving group, so H plus X minus effectively. So a base will assist in the removal of the proton, and then the leaving group will come off. That takes us back to palladium 0, ready to go around again. So that's how the catalytic cycle works. And in fact, a lot of the catalytic cycles we'll see in this and the next session have common features. There'll be an oxidative addition, and at the beginning there'll be a reductive elimination at the end, and there'll be some organic transformations happening in between. This diagram over here is just really to show you to say a little bit more about that rotation, just to draw it in Newman projection terms. And that, if you like, as this rotates, to put that hydrogen in the syn position, that will determine the geometry of the new alkene that's formed. In this particular case, the way I've drawn it, then you'll see that the geometry change overall is replacing this hydrogen by that organic group, with maintenance of the rest of the substituent positions around the double bond. So the key points here are: start with an oxidative addition, do an addition across an alkene, or a migratory insertion of an alkene into the palladium organic group bond. Adjust your adduct so that there is a possibility of a syn elimination of a palladium hydride, and then regenerate by reductive elimination the palladium 0 complex. And so we've gone from this red organic group with a leaving group and this blue alkene to this coupled product. So we think about some aspects of that. The regiochemistry, it's a carbopalladation, so it's addition of across an alkene of an organic group on the palladium and the palladium itself. So you can call that a carbopalladation. Could give a mixture of intermediates. In other words, if you have an unsymmetrical alkene like that, which end will the palladium go to, and which end will the organic group go to? Tends to be substrate controlled. In other words, tends to be determined by the substituents you have on the alkene. The beta hydride elimination step must go by a syn periplanar mechanism, so the palladium must have a hydrogen syn to it. And as we'll see, that may cause the alkene not to end up in the same place as it started, because there isn't a hydrogen, or there isn't the possibility of that rotation to put the hydrogen in the right place, so it has to eliminate with a hydrogen from a different carbon. So the regiochemistry, in other words, which end the palladium and the organic group add, tends to be dominated by steric interactions. So more often than not, the organic group is placed furthest from the bulky group on the alkene, with the possible exception of some electron-rich alkenes. So here, if you look at this alkene with a withdrawing group on it, the organic group couples to the remote position almost exclusively. The same if you have a phenyl or an aromatic group on one end of your alkene, the remote position, the least substituted position, tends to be almost exclusive product. If it's an alkyl substituted alkene, again the least substituted position is the majority product, but you can get mixtures. So 80-20 is just a typical mixture, it's not always 80-20. With a di-substituted situation, it will depend on the two substituents, but here's an example. If you have an alkyl group and a phenyl group, still the least sterically demanding group, the methyl group, addition next to that, or at that end of the alkene, can dominate. So that's something you have to consider. And another on the top here, let's say you get addition to the end of an alkene, I'm implying that that's the most common thing, then you've got a palladium which can actually eliminate palladium hydride to give the alkene back where it started, or the other way, and sometimes, if the positions where the eliminating hydrogens are situated, if those have two hydrogens, then depending on which hydrogen is eliminated and which side, you'll get different regioisomers, and you can get different geometric isomers depending on which H's are involved in the elimination. So ideally you'd like to be able to pre-plan that by fixing limited possibilities, and some of the examples I show you will be like that, where the elimination takes place because that's the only way it can go. So here's an example of a Heck coupling that's intramolecular, and we've got a sequence of Heck couplings occurring. So here's an iodoalkene. We'll get initial oxidative addition into that carbon-iodine bond to give an iodo-palladium complex at that position. Then that palladium is looking to find an alkene or alkyne to react with. We'll go for the more electron-dense alkyne. Complex to it sideways on at first, then oxidatively insert, or put it another way, add across the alkyne. That's, if you like, a first oxidative insertion, a first Heck reaction. But then in this case, because there is another alkene in the molecule, we can get effectively a second Heck type reaction to form a second ring. So this new iodo-palladium complex can complex sideways on to the remaining alkene and then add across it. Now this time it adds to the more substituted end of the alkene because it's easier to form a 6-membered ring than a 7-membered ring if it added to the outside end. So here, what I said about adding to the least substituted end of the alkene is overruled by the preference for a 6-membered ring over a 7-membered ring. And then a palladium hydride elimination to finish it off. Now there isn't any problem with the palladium hydride elimination. It can only go one way because it's a terminal position, and there's rotation around the the carbon-carbon bond that will allow the palladium to be syn to the remaining hydrogen that it's going to eliminate with. So I think that's a good illustration of how you can design, in this case, a cascade reaction, a tandem reaction, to produce two rings at once. The palladium catalyst here is palladium 0 straight away, so it's not a pre-catalyst that needs to be reduced. This example uses palladium 0 anyway. 3 mol%, that's reasonably high, but not too bad. And the base there is helping with the oxidative elimination at the end of the cycle to get rid of the H, or it'll be HI in this case, to regenerate the palladium 0 to go around the cycle again. The bottom sequence is showing another similar situation where lots of sequence of rings is being formed. Here 4 rings are being formed, but it's the same kind of principle. Here is the alkenyl iodide, drawn in a funny geometry, but otherwise drawing the picture gets a bit difficult. But the initial oxidative addition takes place down here. That organopalladium complex adds across the first alkyne to give a new one, which then adds across the second alkyne to give a new palladium complex, which adds to an alkene here, which gives another palladium complex, which adds to the final alkene, and then it's over on this right hand side here is where the elimination of palladium hydride will take place. So I think those are good illustrations of Heck reaction followed by another Heck reaction, because it's been built into the substrate. So in a sense, what you could say is it's worth the effort of putting together these complex backbones, because you're in one coupling step you're getting a lot of complexity out of a relatively an acyclic molecule. I was going to say linear, but it isn't really linear, but out of a molecule not having any rings in it, you're getting 2 rings in this example and 4 rings here, which is perhaps pushing it to the extreme. But as you can see, it's quite efficient, 76% yield. I think that's just accidental at 76 in both cases. There's no significance in that. Here are some more examples. There's actually an error in this bit of the slide here. That bracket with a 2 round should be on these carbons, not those. It's just kind of slipped in the software when drawing. So I apologize for that. So what is happening is the palladium is oxidatively adding there. That's adding across this alkene. So that's why this should be a single carbon here with then 2 carbons and the vinyl group. So that should be 2, that brackets and 2 should be round there. And then that's the second, that's set up for us, the second Heck reaction in that sequence. This example, oxidative addition to the aromatic iodide, same as in the above, then that aromatic iodide complexes and then adds across the alkene in the 5-membered ring attached. This one is then stuck. If the carbon group attached to the palladium and the palladium itself add on the same face, that will be either both of those will add up to the top face or both to the bottom face of the alkene. But that means you can't get the rotation, so you can't get, that's a sort of a dashed bond, but it's too short to show properly. But what it means, so the palladium is syn to the organic group it brought in, but it cannot become ever syn to the hydrogen that would put the double bond back where it used to be. So this is an example where the palladium is forced to eliminate in the other direction. So effectively the alkene moves from where it was in the substrates to where it is in the product. And that illustrates that if you can't get the syn carbon palladium and carbon hydrogen bond, then you can't get the elimination in that direction, and the molecule has to choose to go the other way. Here's some other, so that wasn't what you might call an unexpected product, although actually you could have predicted it because you can't get the syn arrangement. Here's another one, oxidative addition across here, and this, so AR refers to this group, so that's adding, that and the palladium are adding syn across the cyclopentene, but again, or I suppose, yes, you're not allowed to, you can't do a rotation around the bond here because of the 5-membered ring. So this is another one where the elimination has to go in the opposite direction so that you get what looks like a movement of the double bond around, but it isn't coupling to what was a saturated carbon there. It's the double bond being forced to move around because of where there is a syn hydrogen to allow it to eliminate. Here's one where it doesn't, where a little bit more than that happens. So triflate is the leaving group, oxidative addition of the palladium here, coupling, or then addition I should say, across the double bond here. Then it looks as if the palladium hydrogen elimination ought to take place, can't take place, well, that's right, it can't take place where the alkene started out, could go the other way. So you'd expect to find this product. In fact, for reasons that I don't think are well understood, palladium hydride actually re-adds to this alkene, but with palladium at the opposite end. Here it was at the top left-hand corner of the ring. Then it's assumed that it adds again, but in the opposite orientation, and then eliminates in a new direction, then in fact adds again and eliminates again. So the alkene has effectively warped around the ring. Now that must be because this product is more thermodynamically stable than that one, but I'm not quite sure how you predict that. So occasionally you can see this sort of thing happening. It's unusual, but when you see it, then you have to understand that it's probably thermodynamically driven, and you've got reversible palladium hydride additions which could, in certain cases, allow the double bond to walk further away than you might expect. So, say that again. First of all, that there's the elimination where you can't eliminate where the alkene used to be. You can eliminate the other direction. That's what you might expect. But then you get palladium hydride readdition in the opposite orientation to the way it just eliminated. Then in this case, it's then eliminating in the opposite way to which it, to the way it was formed, and then doing that same addition, elimination in opposite direction for one final step. So that has to be thermodynamically driven, but I don't know that you would predict that before you start on that sequence. So that's the Heck reaction. And now to finish off this session, Stille coupling. Okay, we have an organic group carrying a leaving group again. What we're now doing is coupling that to a double bond carrying a tin residue. Now in the Heck reaction we were going to add across a double bond and then reform the double bond. Here we're going to get a direct coupling between this alkyl or this organic group and the carbon carrying the tin. And that can't happen directly, so it's got to go via the intermediacy of a palladium catalyst. This is a very generally written equation. You can also do that coupling where the organic group and the carbon carrying the tin don't couple directly, they're in between them you get a carbonyl group. So that's if you do the reaction in the presence of carbon monoxide. So it's effectively R group is usually benzylic, alkenyl, aryl or allyl, so this is usually an sp2 coupling to an sp2 position, so an sp2 coupling. And you can, as I say, get effectively an insertion carbon monoxide between them. So here's just a couple of examples of that before we look at the mechanism. So here's an aromatic bromide as the R1X group. Palladium 0, a bit of base, etc. Here's the carbon carrying a tin residue. And so that carbon and the bromide carbon couple together. And another example down here with a triflate as the leaving group. Palladium 0. Note the inorganic salt here, lithium chloride. That'll appear in the mechanism where you have a triflate leaving group, and again this vinyl tin compound, and that couples to the position where the leaving group, the triflate, was. So how is that happening? That's what happens. Now how does it happen? If the leaving group is a halide, this is what the cycle looks like. So we have a palladium 0 complex. Again, it's believed to be either 14 or 16 electrons. No one's quite sure in each individual case, and it could be a mixture. Then we get oxidative addition to our organic group carrying a leaving group, carrying a halide, to give us the now palladium 2 complex with the organic group and the leaving group both attached. You then get effectively a transmetallation. So you've got the other organic group that we're interested in that's attached to tin. It doesn't have to be tributyl tin, can be others, that's why I've put alkyl in there, but a tin, so you've got the group you want to couple attached to tin residue, tin nucleus, and then that swaps. The group that was on tin goes on to the palladium, and the group and the X group, the leaving group that's on palladium, goes on to the tin. So it's a transmetallation. This R1 group is transmetallated from tin to palladium. That's the key step here, because now the two groups we want to couple together are both on the palladium, so you get a reductive elimination which takes you back to palladium 0 for the palladium, but couples together our two sp2 centers. So that's a relatively simple catalytic cycle. It's a little bit more complex if the leaving group is not a halide but is a triflate. Then it's believed you still get the oxidative addition, but you then get exchange of the triflate leaving group for a halide leaving group by addition of, as we saw before, lithium chloride, but a metal halide salt. That gives this complex, which looks just like the one if the leaving group had been halide. We then, as I say, swap the group that's on tin to palladium and vice versa. So a halide ends up on tin. So effectively we're just adding this step in to the cycle that I showed on the last slide. Do the transmetallation and you're set up for the reductive elimination again. So here's got some examples just before we finish. Here's a very simple one. This alkenyl iodide, this vinyl tributyl tin compound, and the palladium oxidatively adds into the Ci bond here. This example shows the carbon monoxide insertion into the carbon-palladium bond here before the transmetallation, effectively. So this is adding a step into the cycle before the transmetallation. Carbon monoxide inserts here to give an acyl palladium complex. Then you get the transmetallation with this vinyl group going onto the palladium, and then reductive elimination to join this carbon to that carbon. And another example showing a coupling with carbon monoxide insertion in it. This is a triflate one. Actually, it hasn't got okay, so in this case it doesn't have the halide for triflate exchange in there. Okay, I think that's the last example I've got there. So that's the end of this session. The Suzuki and similar reactions that are at the beginning of the next session are a little bit like the Stille reaction in terms of the catalytic cycle. We just play games with do we use tin or do we use other metal species here instead of tin. So Stille uses tin, but keep that in mind when I show you the other reactions in the next session. Okay, so that's time to take a break, and we'll come, if we can come back again at 11:30.
Tin.
Sorry, what's the role of?
What's the role of tin there? What's the role
It's
of tin alkane?
Yeah, it's being, well, it's the same. It's the same as in the cycles here. You need to do it won't happen. I mean, nothing happens if you haven't got the tin compound. The palladium compound won't do anything. So it's an exchange between palladium and tin. So that you introduce your alkyl group, your organic group on one metal, and it then moves onto the tin, or moves onto the palladium, I should say. And you'll see in these others that it doesn't have to be tin, there are other options. We'll see, I think, boron, magnesium, and zinc in the subsequent reactions. But they're there for transmetallation. You can form the organic group attached to tin or some other metals, but then you need to transmethylate it onto palladium to do the coupling.
Thank you.
Since we are coming to the end, so I need to have the proper list of the phosphines. So as per my call, this is the list those who have registered through the GIAN portal or otherwise. So please get your names, spellings, and put the name of your institution in the third column. And then put your signature so that I prepare the certificates. So just take 5 minutes and then